there's a portrayal of a dark opening that doesn't include gravity, as it were. It includes quantum mechanics. Dark openings are grandiose gorges that gobble up everything in their way, including light itself. These inestimable Goliaths, framed from the withering remainders of colossal stars, have gravitational fields strong enough to mutilate reality, snaring everything inside their gravitational grip, including time itself. Now a revelation, uncovered by the James Webb Telescope, challenges the crucial basis of our understanding, a torpid dark opening that is a couple of light-years from our planetary system, lying in the depths of space. It's as though nature itself is playing a vast game of hide and seek, hiding these heavenly beasts in the most profound openings of the universe. Exactly how does this revelation cast doubt on our long-held convictions about how galaxies came to be? Does this infinite deviation represent a danger to Earth? So join us as we explore how the James Webb Telescope just distinguished an immense torpid dark opening close to the nearby planetary system. Dark openings are a precarious puzzle. It was a challenge to look for the initial one. Despite Einstein's theory of relativity predicting that they were common, dark openings, as opposed to stars, emit no light of their own, making their size and twist the only properties that can be measured about them. We now have visual proof of dark openings, thus, we know they exist. However, decisive verification of dark openings has been missing for a long while. Cygnus X1 was the first to be seen in 1964. Stephen Hawking and Kip Thorne, two of the foremost experts on dark openings, didn't reach an agreement on whether Cygnus X1 was indeed a dark opening until over 30 years later. Hawking was fairly sure that dark openings did exist. They were, after all, a significant emphasis of his professional life. However, whether researchers could actually find one remained unanswered. Naturally, Hawking was a little restless about the lack of discoveries, so he backed his wagers with his studies. He also mentions that he and Thorne were almost certain that Cygnus X1 was a dark opening by 1975 when the bet was initially cast. They were both 95% sure. By 1988, according to Hawking, they came to an agreement that the bet couldn't be settled until they were both sure beyond a shadow of a doubt. Hawking was eventually forced to concede the bet in 1990 when further observations of the system had gathered enough evidence that it contained a dark opening. Thorne claims that Hawking waited for the perfect moment to concede. 2 Geiger counters were launched into space on a suborbital rocket, which led to the initial discovery of Cygnus X1. A signal was detected by the Geiger counters, which astronomers pinpointed to a system 7,200 light-years away, highlighting a blue supergiant star surrounding another massive object. The second object was also emitting X-rays, which would make sense if it were a dark opening. Much research has focused on Cygnus X1 since it was discovered in 1964. It was the first dark opening in the universe. However, it has more surprises in store for researchers. New examination shows that the dark opening is truly 21 times the mass of the Sun. This object has the distinction of being the largest known stellar mass dark opening ever found without the use of gravitational waves. This new finding raises questions about astronomers' long-held assumptions about dark opening evolution. The stellar winds that blow from a star's surface cause the star to lose mass to its surroundings. However, if we need a dark opening this huge, we must consider a reduction in mass loss experienced by bright stars over their lifetimes. Cygnus X1 breaks records in more ways than one. Its exceptional mass is just one of them. Cygnus X1 has the fastest rotational speed of any dark opening found to date, approaching the speed of light. A dark opening with such high spin also doesn't follow the accepted pattern of dark opening evolution. Although conclusive proof of dark openings has only just been found, it is becoming increasingly clear that they are dispersed throughout the universe. Thus, regardless of whether space experts eventually unravel all the mysteries of Cygnus X1, the first of its kind, its countless relatives undoubtedly still hold many surprises. Less than 2,000 light-years from Earth, researchers have discovered a dormant giant, the Milky Way's largest stellar mass dark opening, with a mass multiple times greater than that of our Sun. Despite being the second closest known dark opening to Earth, the dormant Giant BH3 had remained unseen until found accidentally in a storm of data and observations compiled by researchers from the European Space Agency. GIABH3 is situated in the constellation Ayla, the bird. The team observed something strange as they combed through data from the agency's Gaia mission, which is creating a three-dimensional map of our galaxy. A star that was wobbling 1,926 light-years away indicated that it was ensnared in orbit by a nearby massive dark opening. To confirm the mass of GIABH3, astronomers and ground operators used the Very Large Telescope of the European Southern Observatory in Chile to validate their discovery. They uncovered that once every 11.6 years, the wobbling star completes one orbit around the dark opening. The discovery of the nearby undetected high-mass dark opening came as a complete shock to everyone. GIABH3 is a type of dark opening formed from the collapse of a star, known as a stellar black hole, and it's the largest of this type found in our galaxy. As a dormant dark opening, it isn't actively siphoning energy and materials from a companion star, making it invisible in sky surveys. Stellar dark openings in our Milky Way typically have a mass multiple times that of the Sun, with Cygnus X1 holding the record at 21 times the Sun's mass. GIABH3, with a mass of 33 solar masses, is still small compared to all dark openings. For instance, the central supermassive dark opening in our galaxy, Sagittarius A*, is 4 million times larger than the Sun. GIABH3 is the second closest dark opening to Earth, just behind GIABH1, which is 1,500 light-years away and multiple times the mass of the Sun. Space experts now have more evidence to figure out how stellar dark openings form from the end of massive stars, making the discovery even more significant. Stars with lower concentrations of heavy metals are believed by cosmologists to be the source of even more massive stellar dark openings. Hypothetically, these metal-poor stars, which are primarily made of hydrogen and helium, are thought to experience slower mass loss, leaving more material available to create more massive dark openings when they die. Yet, researchers didn't have a map to draw from until they found GIABH3 and its companion star, which was metal-poor, demonstrating that the star that created the dark opening was also low in metals. Space telescope stargazers have found a very red, supermassive dark opening filling in the early universe's shadow. This discovery dates back to about 700 million years after the Big Bang. As the universe expanded, this enormous dark opening took on a ruddy hue. The redshifted light we observe suggests a thick shroud of gas and dust surrounding the black hole. Lucas Farrow and Addis Citron from the Consum College of Astronomy were able to establish the mass of this supermassive black hole by analyzing JWST data. Its surprising mass, around 40 times that of the Sun, stands in stark contrast to the universe it occupies. The researchers found that this supermassive black hole is rapidly consuming the surrounding dust and gas and is located approximately 12.9 billion light-years from Earth. Initially, the team hypothesized that it was a quasar-like object due to its red dot appearance. Quasars form when large amounts of matter surround supermassive black holes. This matter creates an accretion disk of gas and dust that gradually feeds the black hole. The immense gravitational pull of the black hole heats this matter, producing intense temperatures that cause it to glow. Moreover, these colossal titans eject any material that doesn't fall into the black hole using highly collimated jets. Particles in these jets are accelerated to speeds near the speed of light, accompanied by bright electromagnetic emissions. Active galactic nuclei, AGN, produce quasars, which are so luminous that they can outshine all the stars in their surrounding galaxy. In JWST data, this supermassive black hole appeared as a minuscule point due to the tremendous amount of radiation it emitted. Color analysis suggested it was a strange star-forming galaxy, providing more evidence for the existence of supermassive black holes. Its small size and evident supermassive nature distinguished it from other quasars found in those early days. Even with JWST's powerful infrared capabilities, the early quasar might not have been visible without an effect predicted by Einstein in 1915. Einstein's theory of general relativity states that massive objects warp the very fabric of space and time, which are combined into a single entity called spacetime. This warping is what creates gravity. the curvature of spacetime is more pronounced for objects with greater mass, allowing planets to follow specific paths around stars and cosmic centers. Light emitted by stars also changes. The closer an object is to a mass, the more its path is bent. A foreground object, or lensing object, can alter the appearance or position of a background object by bending light paths. In extreme cases, this effect can cause background objects to appear in multiple locations within the same sky image. Sometimes, the background object is merely exaggerated due to the light being amplified. We call this effect gravitational lensing. With the help of a galaxy cluster known as AL 2744, JWST was able to amplify the light of distant galaxies in the background that would have been undetectable without it. This revealed the red quasar that had initially appeared as 3 red spots. This discovery adds to the growing body of evidence that the early universe was populated with supermassive black holes, which can be millions or even billions of times more massive than the Sun. Now that this phenomenon has been observed in numerous early universe supermassive black holes, it sheds light on the development of both the black hole and the host galaxy, as well as their interaction, still largely a mystery. Like the classic chicken or egg problem, researchers are uncertain whether the galaxy or the black hole came first, how large the first black holes were, and how they grew. Researchers might have found evidence that microquasars, black holes that consume stars, are the cosmic particle accelerators responsible for the unexplained high-energy cosmic rays hitting Earth. These massive black holes consume material from neighboring supermassive stars and binary systems. As the material is funneled toward the black hole, some of it is expelled as relativistic jets traveling at incredible speeds. A microquasar is a relatively mild version of a quasar, both powered by immense supermassive black holes that consume matter in their vicinity. First discovered in 1912, cosmic rays can hit our planet with energies reaching 1, 0, 20, 10, 20. Electron volts, eV, far more energetic than particles accelerated at the Large Hadron Collider, Earth's largest and most powerful particle accelerator. Thus, supernovae and microquasars are being considered likely sources of these high-energy cosmic rays. However, evidence of microquasars accelerating particles to such high energies has been scarce until recently. Using the High-Energy Stereoscopic System, HSS, researchers have begun to identify particularly high-energy gamma rays emanating from the jets of the most powerful microquasars. Smoothly, the group laid out the connection between vast beams and microquasars. This is known as SS-433. The SS-433 jets slam into the encompassing matter, creating a shock front that speeds up electrons to speeds adequately huge to make sense of the particles found in high-energy vast beams, bringing about the production of these gamma beams. However, the acceleration mechanism in SS-433 jets is equivalent to that in a cosmic explosion. Leftover shocks in the previous can push particles to greater energy due to their greater speed. The very strong photons emitted by the SS-433 jets suggest, indirectly, that we shouldn't overlook these objects when attempting to make sense of the most powerful sources of astronomical beams from the cosmic center. SS-433 was actually the first microquasar ever found. Its presence was first uncovered in 1975. It was named SS-433 after being included in a 1977 catalog of celestial bodies, then rising to notoriety when science fiction creator Arthur C. Clarke named it as one of his 7 wonders of the world. A white supergiant star and a black hole with a mass around 10 to 15 times that of the Sun comprise SS-433, which is situated at the center of the supernova remnants known as W50, located around 18,000 light-years away from Earth, and is warmly called the Manatee Nebula. SS-433 has been the subject of broad research for many years. The two are separated by about 15 million miles and orbit one another roughly once every 13 Earth days, with a distance of something like 1/3 the distance between Mercury and the Sun. The star companion of the black hole in SS-433 can be stripped of its outer layers by the colossal gravity of the black hole. A portion of this stripped material is actually funneled into the black hole, while the rest forms an accretion disk around it, utilizing very strong magnetic fields. Different parts of the material are attracted to the black hole's poles. The subsequent outflow of material is then launched at a speed roughly 26% lower than the speed of light. These jets swirl in a corkscrew-like pattern and are so powerful that they even shape W50. The W50 supernova remnants were formed when a colossal star burst around 20,000 years ago. The two lumps or protuberances caused by the microquasar within W50 give it the look of a gigantic manatee, which is the justification for its dynamic moniker. Radio waves that are around 1 light-year distant from the source can be used to identify the jets of SS-433. Eventually, they fade until they are no longer visible due to energy loss. Inquisitively, these relativistic jets re-emerge in high-energy X-ray photons around 75 light-years from where the microquasar originated. The group reasons that this demonstrates that the particles ejected from the black hole are being pushed to even higher energy and speeds by something within each jet. The 5 Namibian telescopes that make up HESS were utilized to study these intriguing gamma jets coming from SS-433. And the results showed that the binary system was further away from the source of the greater strong gamma rays. The group inferred that gamma rays, which are particles of high-energy light, are best understood through rapid shock-accelerated electrons in two areas around 75 light-years from the central axis of SS-433, where shocks are bending jets into a tight funnel and enhancing the energy of the accompanying particles. The group will now attempt to uncover the remaining secrets surrounding this captivating microquasar. As part of this process, they aim to identify the source of the jets and shocks that have been detected far from the binary system from which they originated. Moreover, the group will seek to generalize their understanding of microquasar jets to jets emitted by larger quasars powered by really massive black holes. Furthermore, although these results clearly highlight a potential origin for high-energy cosmic rays, they do not yet solve the cosmic mystery that has endured for a long time. Black holes, exomoons, dark energy, and much more will be among the objectives of the James Webb Space Telescope in the coming years. Investigating early-stage quasars and the characteristics of the first black holes are two of the many topics covered by JWST's Cycle 3 of very massive black hole observation missions. Over the course of billions of years, researchers are hoping to conclude how these black holes might have impacted universe formation and how these cosmic behemoths achieved their tremendous masses before the universe was 1 billion years old, which may be uncovered by JWST examinations of very large black holes in the early universe. With the help of MIRI, we can see if a massive atomic cloud that formed 13.2 billion years ago might have collapsed directly, leading to a heavy black hole seed, while also explaining how the universe expanded so rapidly. Analyzing objects from the early universe is one of the main tasks of JWST. While the primary objective of JWST's design was to concentrate on objects far away, the observatory will also be used to study objects within our solar system during Cycle 3.